We have been studying the orbits of comets for hundreds of years, since the days of Edmund Halley. In that time, we have found that comets passing through the inner solar system as we know them, with sometimes spectacular comas and tails, all seem to originate from our own outer solar system. And we also know that comets get kicked out of our solar system entirely, suggesting that wandering interstellar comets should not be rare. Yet in the centuries since Halley's time, we have yet to see a single interstellar comet following a hyperbolic trajectory. But now we're starting to get some clues as to why that might be. The object known as Oumuamua was discovered to be on just such a trajectory and must have originated from the interstellar medium rather than the outer solar system. But Oumuamua was strange, perhaps fitting for an object not of this solar system. It didn't outgas as a comet would, but rather it seems to have outgassed only enough to cause an acceleration in the object's motion, sort of like a natural thruster as the icy volatiles in the object were heated. What does this all mean? My guest today is studying just that, and coming up with answers about why Oumuamua is so strange.
Welcome to Event Horizon with John Michael Godier. In today's episode, John is joined by Darryl Seligman. Darryl graduated from the University of Pennsylvania with degrees in mathematics and physics. He is now a graduate student and Gruber Fellow at the Astronomy Department at Yale University. His primary study is theoretical and computational astrophysics, having worked on a variety of topics that are broadly related to planet formation. Most recently, he worked on the interstellar asteroid Oumuamua and dust plasma instabilities.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Darryl Seligman, welcome to the program.
Thanks a lot for having me.
Now, Darryl, you're working with probably the strangest object that we've seen since, I don't know, since somebody took a picture of a black hole here. It's Oumuamua. Oumuamua is the first detected interstellar object. This is not from this neighborhood. Tell us what originally brought you to Oumuamua. What piqued your interest to jump into the debate on this object?
Yeah, right. Well, as you said, this is probably one of the most interesting scientific discoveries that's happened in the last couple of decades, to see the first interstellar object that's passing through the inner solar system up close. Basically, I mean, if you did a conference proceedings or paper search on ADS for how many articles were written about Oumuamua following the initial announcement back in a couple years ago now, in fall 2017, you would see that there was a huge flurry of papers written as quickly as possible by many people worldwide. So this sparked kind of global attention from scientists, but not just scientists, also global media attention as the first interstellar object ever. So it was just after, when I heard about the object, it was just natural for, well, there's also my advisor, Gregory Laughlin, who's a professor here at Yale University, but we just immediately were interested and we had to start figuring out what was going on with this weird object. And not only is it because it's the first interstellar object ever detected, but along with it, it was nothing like what we expected the first interstellar object to be. So if you actually went back and looked, there have been papers before Oumuamua was detected about trying to understand why had there not been a detection of an interstellar object yet, because it's pretty natural to imagine. We know that in our solar system, giant planets like Jupiter and Neptune, which have enough energy, we know that as they formed and the solar system has comets and asteroids, we know that Jupiter and Neptune has ejected interstellar comets and asteroids into the galaxy. So it has long been thought that their galaxy should have interstellar objects scattered from other Jupiter or Neptune-like planets around other stars. So it was interesting that there were people writing papers about interstellar objects before we even detected one.
I've actually read several papers that I think predated this that suggested that maybe Jupiter had captured some interstellar objects in the past, and that some of these objects floating around the solar system aren't from here. What differentiates an interstellar object from an Oort cloud comet or something like that? What do we expect would be different?
Right. Yeah. No, that's an excellent question. So yeah, there were papers before Oumuamua about the idea is basically that interstellar object passes through the solar system, but it comes in such a way and it gets close to Jupiter that Jupiter's gravitational influence can capture it and bind it to the solar system. Now, I mean, you would naively think this is a rarer event because it has to pass pretty close to Jupiter. But at the same time, once an interstellar object gets captured, it's captured for life. So then you have the fact that you have a lot more time for that to happen. So does that make sense? You can kind of see them from a long time ago. So what's different about those objects is actually pretty interesting. There was a pretty interesting astrophysical journal letter by Amir Siraj and Avi Loeb that was talking about finding possible bound interstellar objects that were bound to Jupiter. And basically the idea is that, things that form in the solar system, I mean, this is very first order. It's a little more complicated than this, but things that form in the solar system should all it should all orbit in the same way around the sun in the same way. But you can basically try to identify these bound interstellar objects if they have retrograde orbits. So if they're moving differently than all of the other small minor bodies in the solar system.
So retrograde orbit, meaning that it's going opposite of everything else in general.
Exactly.
Yes.
Yeah. So that's so basically those bound interstellar objects, if they're because they can come into the solar system from any direction, they could be orbiting in any direction. So if they're orbiting opposite of what all the other bodies in the solar system is doing, then that's a clue that they're interstellar. That's not definitive proof though. So although there could be a lot of these bound objects, it's going to be tough to definitively say whether or not these objects were interstellar in origin. However, with something like Oumuamua, which is on a hyperbolic trajectory, which means that it basically comes in with not enough, it doesn't get bound, it leaves, and it never comes back, that's definitively an interstellar object.
It's sort of like a bullet passing by.
Exactly.
Yeah.
But a bullet that then gets, pulled in by a string to some central point. So at this point, it's like a bullet that passes by, but then the sun's gravitational influence is pulling it towards it. So its orbit definitely gets deflected depending on how close it gets to the sun.
Did you see the recent paper? I think it was Loeb and I don't know who else who's on the paper, but that maybe some of the meteorites may actually be of interstellar origin, and that maybe sometimes occasionally these objects hit Earth and we have samples of them and we just don't know it.
Yeah, that was actually the same. The first author is the same as on the other paper. That's Amir Siraj over at Harvard also. Mm-hmm. But yeah, no, that's very interesting.
And it makes you wonder, not only could we detect interstellar objects, but we have ways to actually study them. Now, you are also involved with this idea of actually intercepting an interstellar object. Tell us about that.
Yeah, so this was the first paper that I wrote with Greg. This was immediately after the announcement, the Minor Planet Center announcement of Oumuamua, right? So these minor planet circulars come out, and you see they come out every time there's a detection of a minor planet or a small body near Earth object. But then this one with Oumuamua had an eccentricity of 1.2. That means it's on a hyperbolic orbit. That means it's unbound. And so immediately after that, everyone got interested in it. And the idea was just, what we were thinking, okay, so if it turns out that we're actually not very good at detecting these objects. Not that our technology isn't very good, but these objects are simply extremely difficult to detect because they come through extremely quickly, they're small, and they're not very bright. So we only detected Oumuamua as it was leaving the solar system. This is it was a month after it came to its closest approach to the sun. So we detected it as it was leaving. And the fact that we detected it at all implies that there are tons of these objects out there that we're missing because we're just not very good at detecting these objects. So if you do a kind of rough order of magnitude estimate, you say, there should really be one of these interstellar objects passing through the inner solar system at any given time that we're not detecting. But when we have better telescopes online, we will start detecting more of these objects. So it's kind of imminently important to characterize this population, figure out how many more we're going to find. And then once one of these objects comes through and you detect one, something like Oumuamua, right? What do you want to do ideally? Well, ideally, what you want to do is have a rocket or something ready to go, launch it and orbit match, land on it, sample, return, and come back. Because then you can have physical samples from the first interstellar, so something that formed outside of the solar system that came to our solar system. You get physical samples up close, in situ observations of this, and you could do lab experiments on it. Of course, you have the constraint of the rocket chemical propulsion that we can get today, right? So the main problem is you could potentially get to one, but these things move so quickly, it's impossible with today's rockets to orbit match it, let alone land on the object. So what we did was we kind of thought of all of those prospects and said, what is feasible to do based on today's best case rocket capacity? And we realized that orbit matching is going to be impossible, but doing an interception, just like an impactor, like the deep impact mission that went to the comet Temple 1,
yes,
that would be ideal to do, because there suddenly you don't actually need to orbit match. All you need to do is jump in front of it. And because the thing is because it's moving so quickly, all of the energy in the impactor is coming from the orbit of Oumuamua, or the interstellar object itself. Then what's also cool about that is because your bias to detect the ones that we're going to detect are the ones that come close to the Earth. You don't actually need to give it that much energy, give a rocket that much energy to demand an interception. So we asked the question in that paper, just, how, if we had something like LSST, the upcoming telescope that's going to see the entire sky.
Yes.
And go much deeper, so see much fainter objects than pan-stars. How much, if we had detected the object earlier, say when it's coming into the solar system, would it have been possible to send a rocket interception mission? And amazingly, so something like Falcon Heavy should get this thing called delta V, that's just the change in velocity from the Earth that you would need to give a rocket to demand an interception. So Falcon Heavy, if you use the payload to something like Mars and you sit it at L1, that's just kind of sit it in a Lagrange point. Using that, you should be able to get something like 15 kilometers per second of delta V. Mm-hmm. It turns out if we had sent an interceptor mission in July, so if we detected it back then we would have easily been able to intercept Oumuamua itself with a delta V of 4 kilometers per second. So we asked the question, this would have been not trivial, but definitely doable with today's rocket inventory for Oumuamua. And then we did these simulations of how many is LSST going to see, and we found that LSST should be seeing a handful, about 10 of these objects, up to 10, several of these objects every year. And then we asked the question, just how many of these are you going to feasibly be able to intercept? So how many come close enough and require delta V that's within reason of something that we could do? And that figure turned out to be something like, it's an order of magnitude estimation, but something like it's about a 10-year wait time between objects that you'll be able to intercept.
We live in an amazing age, where we have things like Falcon Heavy, but we're on the cusp of some crazy rockets like Starship and what Blue Origin is doing. How does that change the equation? With these gigantic Saturn V class rockets that seem to be coming quickly, how does that change things?
Well, that could totally revolutionize it. Everything that we want to do going forward is lowering that number down, right? So getting less than, a 10-year wait time is not bad when you think of the timeline for missions that have been approved.
Sure. How long did it take to get to Pluto,
Right, exactly, yeah. The new class of rockets will only improve that number. So it's an extremely exciting time between the new class of rockets that'll increase the delta V that's available to intercept something like this, and complementary to that, having something like LSST imminently coming online that will be detecting many more of these objects. Now, it's interesting, the European Space Agency has recently selected the Comet Interceptor as their upcoming mission. So it's an extremely exciting time for in situ observations for interstellar objects, these new class of astrophysical objects.
Now, the LSST is going to give us basically an all-sky survey pretty much every day,
Yes.
or every day and a half, something like that. So this is eminently capable of detecting anything, that's cooking through the solar system like Oumuamua. And I would expect that we're going to see a lot of these objects, and we'll have to do a pick and choose on what what to go look at. When is the LSST going to be? When is first light and first science on that instrument?
It's not for a few years, and the timeline is not completely concrete, but in a couple of years, it should be online, and it should have first light.
And it should see something fairly quickly, right, as far as interstellar objects go?
Yeah, I mean, if what you have to do is compare it. So what we currently have is, and Karen Meach, I know you've had on the show and can tell you more about this, but the Pan-STARRS survey is similar to LSS, similar, but in the lifetime of Pan-STARRS detected one of these objects. With LSST comes online, it can see much, much deeper than Pan-STARRS, orders magnitudes deeper. You're going to start seeing many of them, so it's very exciting.
So we have something weird going on with Oumuamua, and that's its geometry. It looks like it could be a pancake or a shard or something like that. But then we go out in the outer solar system with New Horizons, and we look at Ultima Thule, and we see that these objects are kind of flat. Is there a sense within science right now that maybe objects maybe they're really flat? Maybe that's normal. And that even though we don't really see too many objects in the solar system that have that kind of geometry, maybe that's what happens to objects that are far from their stars. Can you go into that?
Yeah, that's a really interesting point. And we could also probably get back to this point after we talk about the outgassing and the non-gravitational acceleration. But I will say that, so in my recent paper with Greg and Konstantin Batygin over at Caltech, we generated light curves for a few sets of model geometries. So you talked about the elongated shape, right? That shape is inferred from the light curve itself. So all we have is the light, and when I say light curve, I mean the brightness variations, the changes in brightness over time that was observed. And those brightness variations, even though they occurred you saw kind of a periodic bright to dim back and forth. Those bright to dim, the amount of light that was reflected off the surface changed by a factor of about 12. So you infer that it must be extremely elongated and have an extreme aspect ratio. That's what you call it, just the size of the one axis to the other. You infer that because of this extremely large change in the brightness that you're seeing every couple of hours when we were observing the object. And then you can interpret that, okay, say it's something long and spindle-like, like a cigar, you can imagine that if it's tumbling as it's coming past us, when it's kind of edge on, you're seeing kind of like the brightness minimum, but then when it's head on, you're seeing the minimum, but when it's edge on, you're seeing the maximum. So that's just to say it must be, a weird geometry so that you can explain those brightness variations. So we created some synthetic light curves of different geometries tumbling, because it's not clear what the geometry was in our letter. But there was recently a paper submitted to the monthly notices that did a much more impressive job than we did and basically hammered down what the shape is. So what this paper did, it was on the archive a few months ago, but basically ran a huge number of computer simulations to simulate all of these different synthetic light curves for different geometries, and suddenly realized the shape has to be something like the definitively most probable shape for Oumuamua was a 6-to-6-to-1 ellipsoid. So that's basically like a big pancake.
Big pancake. Now, and that actually was sort of hinted at in Meach's work, right? They sort of concluded that's probably what we were looking at is this big pancake, and then
it was either basically either a pancake or a cigar,
right?
Something long and spindle-like or pancake, but the pancake is definitely right.
And you say a 6-to-6-to-1 ratio, so it's basically pretty much a classical pancake, right? I mean, how you would expect, how you would describe a pancake.
And you know what's kind of beautiful about this is that pancake geometry, in retrospect, that maybe should have been clear clearer to us that it should have been the pancake, because based on what you saw on the light curve, you see that the factor of 15 to 12 brightness variations happens every 4 hours, and it gets very dim every 4 hours. And if it was something like a cigar, it's a lot less likely that would happen, because it's a lot harder to catch the deep minimum looking edge on of a cigar than the minimum of just looking edge on at the pancake, if that makes sense. That's the kind of physical interpretation for it.
It does make sense. Now, we have to take a break. I am joined today by Darryl Seligman of Yale, and be sure to like, subscribe, and hit the bell. We'll be back in a moment when we're going to talk about how this object managed to accelerate. Darryl Seligman, welcome back to the program.
Thanks for having me.
Now, Darryl, the weirdest thing about Oumuamua for me is that it seems to have accelerated on its way out. Now, this is not something that's, I mean, on its face, it sounds crazy, but comets do this because they have outgassing jets and things like that. So could this be an interstellar comet?
Yeah, okay. You kind of hit the nail on the head. This is the maybe weirdest thing about Oumuamua, right? And that's that as it was leaving the solar system, it accelerated with non-gravitational acceleration. So in addition to the acceleration that it felt from the sun, we found by measuring the astrometrically, that's just measuring the position of the orbit, that there must have been an extra force that was acting on the object as it left. So it caused a non-gravitational acceleration. And so what people basically, Karen Meach and Michelle, what they discovered in their Nature paper that announced this non-gravitational acceleration was that the force that pushed on the object was kind of constantly pushing away from the sun. And so immediately that was interpreted as outgassing. Like you said, could this be an interstellar comet? So what comets do, what's interesting, they have comets and asteroids in the solar system. You're probably familiar with beautiful pictures of comets when they have these cometary tails or comas. And you see them kind of streaked across the sky and very bright. What that is, what's actually going on there is you have comets that have ice in them. So there's icy volatile material is what we call it. But what happens is that in kind of outer space, when the sun heats up the ice that's buried in these comets, what happens is the ice heats up and sublimates. So that means that the ice turns immediately into gas. And that produces a large outflow is what you call it, or you just called it a jet. And in that, outflowing amount of gas, you'll have small, tiny dust particles that reflect sunlight. So the cometary tail that you're seeing is dust particles entrained in the outgassing, in the jet. Now, this is common to happen to solar system comets, and not only is it common, what you'll see is that the outflow erupts off the surface, and then the object will exhibit a non-gravitational acceleration. So solar system comets will speed off and will have non-gravitational accelerations due to the outgassing, and you'll see them kind of change their spin, how fast they're spinning. So when the Oumuamua it's actually kind of interesting, when it was announced that it had non-gravitational acceleration, this was immediately thought to be evidence for outgassing. But the weird thing about that is not that the first interstellar object would outgas. So that's actually what you expect. So the difference between comets and asteroids is that asteroids don't have any icy material in them. So they don't outgas and they don't produce a cometary tail. And what's weird is that if you take the hypothesis that, okay, this first interstellar object is something like a solar system comet or asteroid, but from another solar system that got ejected by something like a Jupiter or Neptune around another star, that thing must have ice in it. So the fact that it had no cometary tail was extremely weird, because you're trying to understand, how could this be the first interstellar planetesimal that got ejected if it doesn't have ice in it? So when we detected the non-gravitational acceleration, it was almost like, oh, it must have outgassed. Now that makes a lot more sense, because now it means that there must have been volatiles in it. Does that make sense?
Yes, and let me ask you this. Now, we have been tracking comet trajectories for 3 centuries since the 18th century. And we have never seen something that appeared to be an interstellar exocomet.
Right.
And there's some question about where Oumuamua might have originated in its star system, that maybe it was actually closer and not really an analog of the Oort cloud object, right? So why is it that we don't see spectacular, pristine interstellar comets coming through the solar system all the time, with giant great comet status. Why don't we see that, do you think?
That's really an excellent question. And all you can do is just take the kind of numbers that we have now and say the fact that you kind of have to flip it on its head. The fact that we haven't seen one based on how, sensitive we are to seeing those things or how close you'd expect them to come, how many there should be out there. So yeah, that's a great question. I mean, the fact that Oumuamua itself didn't get much brighter. Something that's interesting is that you actually, so you have to be careful, right? Because when you see a solar system comet that gets much brighter, like I said, you're seeing the outflow, but what you're seeing is micron-sized dust particles. So you're seeing like small dust particles that are reflecting light, but it's only a certain size. There's a kind of limited size range of the dust particles that can actually reflect the sunlight back at us. So is this telling you that the outflow of interstellar comets is just in composition different than what you see in the solar system objects? And, maybe it's just the fact that there are a lot of interstellar comets that come through, but they don't produce as big of a coma. So I don't know the answer to that question, but it's a fantastic question and something like LSST detecting more of these objects should shed more light on.
It's interesting because if you look at like Oumuamua, it's reddened from being out in the interstellar medium for a long, long time. And you got to wonder, could that process of being out there traveling the galaxy, could that degrade those volatiles and things like that? I mean, could it just be that the interstellar medium turns comets into asteroids?
Are you sure you don't have a PhD in astronomy?
I have no degree whatsoever in anything.
So actually, that's exactly right. So this is funny because in my first paper, when we proposed the interception mission, we were trying to this was before the non-gravitational acceleration was announced. So we were trying to say, okay, this thing has to have had volatiles, because if it was a scattered planetesimal, there's no way to understand it without having ice in it. So is there a way that you could have volatile material in Oumuamua and still not get a coma? And so what we did, if you look at my paper, it's like I think it's the first figure. What we did was we said, okay, it's traveling through the interstellar medium for millions of years. What happens is it gets exposed to these things called cosmic rays. These are cosmic rays and high energy photons. So photons from, hot stars like UV photons. And what happens there, we know this from lab experiments, is that if you have icy material and you expose it to high energy radiation, that icy material will break down into something like lunar regolith. And so what's cool about regoliths, this lunar regolith is fantastically good at insulating material. So what we said in the first paper was, how much insulating regolith could you get, which just comes from exposure to galactic cosmic rays? How much of that regolith could you have on the surface of the comet of Oumuamua to stop intervolatile material from heating up and sublimating? And surprisingly, we actually found, so regolith is so good at insulating, so good at not letting heat through, that if you look at the plot in my paper, you only need something like 10 centimeters or less of regolith to protect an entire Oumuamua full of ice from sublimating. So that's totally possible. So that was kind of our working hypothesis for what the reason that. So we were saying, the main reason to send an interception mission is that this thing must have volatiles. We didn't see a coma because the volatiles were kind of safely in this crust of regolith. And so what you want to do is basically exactly what they did to the Temple 1 mission, which is send an interceptor, expose the regolith, take off the surface of regolith, expose the intervolatiles, and then those volatiles will suddenly sublimate, and you'll be able to take detailed spectra from Earth and characterize what's in them. So that was what you described there is exactly what we were thinking before the non-gravitational acceleration was announced.
Now that's cool. So correct me if I'm wrong. All right. So an object floating through the interstellar medium over a long enough period of time can build a coat, what you're saying, the regolith, and that can actually prevent it from being a full-blown great comet as it comes through. It's just sort of sealed.
That's exactly right. And okay, but one thing you have to remember though, before one kind of caveat, it's not a caveat, so that statement is true, but the fact of the matter is that these long period comets you see in the solar system, they're living way out in the solar system. I'm talking hundreds of AUs. And those things also get exposed to high energy photons and cosmic rays. So the natural thing to think then, based on our work, was kind of, could there be a large family of dark comets? So comets that have, had volatiles on the surface that broke down and had a similar type of regolith on their surface, and then they pass through, when they come through their close approach to the sun, they also don't light up and produce a coma. And that's, that was something that some people pointed out after we wrote that paper, and it's just totally plausible.
Okay, so my inner dinosaur is telling me that would be hard to detect, and maybe something like that could hit Earth.
Yeah, but you would detect, that would be hard to detect in the same way that Oumuamua was hard to detect. Right? So something that is going to come close to, they'll, if it's on a trajectory that's going to hit Earth, they will detect it.
Except Oumuamua was found after it had passed the orbit of Earth anyway. But with new instruments like the LSST, then we have at least some kind of early detection. But Pan-STARRS should do that too, I suppose. But
absolutely, yeah. And Oumuamua, remember, didn't come, even though it came close enough to Earth to see it, it didn't come that close to Earth. So yeah, something I think definitely with LSST you're going to detect those. That makes the planetary defense stuff a lot
easier,
more guaranteed. Yeah, easier. But
yeah,
things that are on trajectories to hit Earth, you'll detect them.
Although we should probably even beyond LSST, we should probably be looking much closer for objects that might strike us, because it's happened.
Yeah.
Now, all right. So once we look at this object and we can intercept it, right, or any interstellar object, we get into interesting questions. Things like composition. What does an object that formed halfway across the galaxy, conceivably, what does it look like? How is it different from objects that we see in our solar system? And we get into things like organics. What does that look like? The stuff of life, or things like what isotopes and differences. These things could be chemically very different, within reason, of course. It's probably going to be the same stuff, same atoms, but different ratios and things like that would look very different from things we see in the solar system. What do you expect from that, sort of the science side of it? What are we going to see compositionally, do you expect, from intercepting an interstellar object?
Right. So first of all, that's the key question, right? That's the key reason to do one of these interception missions, is just if the amount of interstellar objects that are floating through the solar system that are filling, you got something like 10 to the 26 of them in the galaxy implied by Oumuamua, that means that, these things are, for lack of a better way of saying it, these interstellar objects are being FedExed right to us. So it's an amazing opportunity to kind of characterize the composition of something that formed around another star. And we don't know what to expect. So the first thing you can kind of guess at is what we can do is look at other stars and kind of look at the light that they produce and infer things like compositions, chemical compositions of the surfaces of other stars. So that we kind of know. And then you kind of expect that things that form around a star are going to form from the same material as that star. So you could kind of guess that, planets and planetesimals, when I say planetesimals, I mean kind of small things like comets or asteroids, but around other stars, should roughly have the composition of that host star. But besides that, we have no data about this. This is a completely new area that suddenly we're getting building blocks of these planets and stars kind of sent to us. So I don't know exactly what to expect, but I can sure say that it will be scientifically interesting to figure it out. And it's an amazing opportunity, and it'll probably be different than the type of chemical compositions that you see in the solar system. However, you can talk a little bit, we can talk about this too if you're interested, but based on the outgassing and stuff like constraints from stuff like Spitzer, we could talk a little bit about the composition of Oumuamua itself.
What do we know about that?
Yeah, so this gets back to that outgassing story, right? what was another weird thing about Oumuamua was that the non-gravitational acceleration really looked a lot like cometary outgassing because it's always pushing away from the sun. That's what a cometary outgassing would do. You just kind of think about it. The sun heats up the surface of Oumuamua, heats up the volatiles sublimate, and then they'll sublimate in the direction of the sun, if that geometry is kind of clear to you.
Yes.
And then what that does is that it's just, equal and opposite force type thing. Oumuamua is going to be pushed away from the sun. So it really looks like outgassing, but then the weirdest thing, if you look at, it's a paper from last year led by David Trilling at Northern Arizona University. They actually looked at, they tried to observe Oumuamua with the Spitzer Space Telescope. Now, Spitzer is a space satellite that has cameras that are sensitive in the infrared bands. So in looking specifically at infrared light, and they couldn't detect Oumuamua with Spitzer at the same time that they were detecting it with other telescopes. So the fact that there was the weird thing about that, though, is the fact that you don't see it in the infrared means that there was very strict limits on how many carbon-based molecules were in the outflow. So if there had been, another way to say that is there had been stuff like carbon dioxide or carbon monoxide that was outgassing from Oumuamua, Spitzer would have seen that for sure. So what you can say is there was very little carbon in Oumuamua. So then if it was outgassing, if you say it's something like water, which has no carbon in it, that implies that the carbon to oxygen ratio, so that is how much carbon there is with respect to oxygen, has to be extremely small, which is something that we talk about in our paper.
That's interesting because with very little carbon, that's very little carbon compounds.
Yes.
But yet it looks reddened, which usually sort of suggests that, doesn't it?
Yeah, but there are other ways to get reddened stuff. I mean, regolith is kind of red. If you look at regolith, that would look based on. We're not talking red like an interstellar Tesla, right? Like it basically looks a little reddened, similar to how bodies of small solar system objects look.
I see.
So there are lots of ways to get something like that. But yeah, that is true. Another thing that was weird about the outgassing though, so a lot of times if you look at big solar system comets, so there's a handful of comets that we actually have we have information about how they outgas and information how the comet itself spins around its own axis. Is that clear?
Yes.
So something that's weird though is if you look at solar system comets, a lot of times what will happen is as it outgasses. So imagine taking something like a baseball bat. If you hit the baseball bat right in the center, then it's going to move away from you. But if you hit the baseball bat anywhere besides the center, it's not only going to move away from you, but it will also start spinning up. And you'll see some solar system comets, once they outgas, if you imagine an outflow comes off the surface, that's kind of like hitting a baseball bat at some weird point, it should start spinning up. So after the non-gravitational acceleration was announced, it was interpreted to be outgassing, but then some people started saying, well, it can't be outgassing, because if it was outgassing, Oumuamua would have spun up extremely quickly. And if it spins up, one thing about even though the light curve, when you were looking at the brightness variations, even though it got bright to dim by this enormous factor of 12, the period with which this dimming and brightening happened, which is say how long between successive bright peaks, was constant. So it's a little less than 4 hours. So that means that it can't be spinning up. So originally, a couple of people were saying, well, this can't be an outgassing from a comet, like a comet in the solar system, because the object clearly didn't spin up. And so what we did in the paper with Greg and Constantine was to say, take a kind of idealized model of a outflow, but basically just say, okay, just imagine that you have something like Oumuamua, something that's elongated, and then the jet that comes off the surface, let's just say that the jet always comes off the surface towards the subsolar point. So that's the point on the surface where the sun is maximally illuminating. So this is kind of physically motivated. If you look up a picture of something like the comet 67P, you'll see that this comet 67P itself, you'll see, because they went to that comet and took pictures, and you'll see the sun shining on the comet, and the outflowing coma that you're seeing in those images is going right in the direction of the sun. So what's happening is just the sunlight comes on to the surface of the comet, And where on the surface it's heating up maximally is where the sun is shining most. So that's the part where the ice is going to heat up and be able to sublimate. So we just kind of said, just imagine it's an idealized case where Oumuamua is just, always tracking, the jet is always tracking the positions of the sun's maximal shining. But then amazingly, in that kind of scenario, we did this both computationally with three-dimensional tumbling simulations, but also you could do it mathematically in an idealized two-dimensional case. The system reduces basically to the pendulum-like equations of motion. So it's not exactly a pendulum, but it's basically a pendulum. And what's amazing about that means that it's total, if it's tracking the subsolar point, if the jet's coming off the surface pointed towards the sun, there's no problem with it not spinning up, because the pendulum doesn't spin up, it's just going to rock back and forth. So we basically have these kind of three-dimensional simulations that we have animations for, where the jet just comes off the surface towards the sun, and then as it does that, it's going to rock it back and forth. But then as it rocks back and forth, the jet moves across the surface.
Can you see that in the light curve, that rocking back and forth? I mean, is that consistent with the light curve issues?
Yeah, and so what we did is we actually used this software that they use to create kind of video games, this computer graphics software they use for video games and animated movies. What we did is render the entire scene, put down the sun, which is just a light in this kind of software, put down the earth, which is just a camera, and then take a picture. And so you could say so you do model how the thing is going to spin, and then at each point in time, take a picture or take a synthetic observation with a telescope, and you can basically see that the light curve, you can make a light curve for exactly what would happen. So not only does it not spin up, but you'll see it change by the factor of 15. And if you get it chaotically tumbling, which just means tumbling around its non-principal axis, then you're going to see light curves that are very similar to the ones that was actually observed. And so we kind of pointed that out and did that for a few model geometries. But then I think I mentioned earlier in the interview, there's a paper on the archive recently that this is for, I think it's like hundreds of thousands of different geometries. And that's how they nailed down the shape. So they basically took what we did and did a kind of much more thorough investigation of what shape could produce the exact right light curve. And that's why I was saying, it's got to be the pancake.
That's cool. Now, so constraining down to the actual pancake instead of the shard.
Yeah.
Which is a big question, that was floating around. What is the geometry of this thing? Now, let me ask you sort of a different question. Once we start looking for these things with the LSST, how many of these objects do you expect are in the solar system at any given time?
Yeah, so the way to answer that question is to think about it like this. We know that we've been looking for these objects. So we've had something like pan-stars. We've had pan-stars, say, roughly observing for about 10 years. Just, this is just an estimate. But based on that, you can say, okay, well, how sensitive are we to observing these objects? Because that they're, if you assume they're all kind of like Oumuamua and as bright as Oumuamua, you can say, how good are we at detecting them? And that implies then what you can say is, how bad are we at detecting them, or how many of them would also be coming through the solar system that we're not seeing because we're just not detecting them. And if you do the estimate, that's saying that because they're moving pretty quickly, there's about one of them in the inner solar system at any given point in time. So with LSST coming online, they're passing through the solar system. They're sitting out there ready for us to find them. We just need more sensitive instruments if we're going to start detecting more of them. But there should be many, many more.
Now, my last question for you is about tracking these objects backwards. Do we have any hope of determining the actual origin, what star system they came from? Or is this just are they like 8 balls in an advanced game of pool? You just can't reconstruct where they came from.
Yeah, that's a really good analogy, actually. It is, unfortunately, there are a lot of papers written on this. Unfortunately, they're more like 8 ball. So there's no hope of taking a single object. So first of all, think about it like this. You've got uncertainty in the orbit itself of the object that you saw. You have to track that back through time. So you can get that back through its trajectory through the solar system. All right, you can do that, okay. But then you take that and extend it out through the galaxy. Your uncertainty bar errors are going to give you huge errors for where it's coming from. But on top of that, they travel through the galaxy for so long, they're just mixed into the chaotic nature of the orbits in the galaxy. But what you can do, so if you think about it like that, yes, you can't take Oumuamua and say where it came from definitively, which host star, if it even came around a star. But what you can do is if you found many, many more of these objects, you could start getting population statistics. So saying overall what the kind of kinematics, and that's, how these objects move, what their chemical composition is, etc.
All right, we are out of time. Thanks for talking with us today, Darryl.
All right, thank you so much. This was great. I really enjoyed it.
I wish you the best of luck in your work.
Me too. Thanks.
Unraveling the mysteries of Oumuamua illustrates that we live in a new era of astronomy. We can now study the goings-on of our own solar system at unprecedented levels of detail, such as pan-stars discovering Oumuamua. This will only get better as new instruments like the LSST come online. We will be able to study the solar system in near real time. This is bound to reveal all sorts of odd phenomena, not just within our solar system, but the universe itself. Few things could be as exciting, and maybe, just maybe, we'll someday be able to visit objects like Oumuamua and learn about other star systems from the comfort of our own.
John,
Yes, Anna?
are you still working on your new book?
Well, I will as soon as I get it back from Schrodinger's possum. Wait a minute. I hope he's not making a nest with it.
The opossum says, it's a very good read thus far.
How can a quantum mechanical possum read?
You'll have to ask him the next time he raids the fridge.
Is that where all my gourmet food went?
You mean the gourmet food that's really open tins of cheap sardines? That's in the bin, John.
Well, as long as he doesn't touch my box of wine.